somewhere out in the vast dark between the stars, in a place no human will ever visit, a great cloud drifts in silence. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. This cloud is wider than you can picture, larger than our entire solar system many times over, and it is the place where stars and planets begin. It has no name yet. It is only gas and dust, moving slowly in the cold. The dust grains inside it are tiny. Each one is smaller than a single grain of flour. They drift in patient swarms, carried by gentle motions that take millions of years to play out. The gas around them is mostly hydrogen, the simplest atom in the universe, mixed with a little helium and a sprinkle of heavier things left over from older stars that lived and died long before our sun was born. The cloud is cold. It is colder than anything on Earth. In some pockets, the temperature falls so low that even sound itself, in any form we know, could barely travel. If you could float there, hanging in the quiet, you would see almost nothing at first. The cloud is so thin that, by everyday standards, it would feel like the deepest vacuum. Yet across enough space, all those whispers of matter add up. A single cloud like this can hold the mass of thousands of suns. Some hold millions. They glow faintly in soft reds and dim blues, lit from within by the few young stars already burning at their edges. From far away, through a telescope, they look like sleeping giants painted across the dark. These clouds are the cradles of solar systems. Every star you have ever seen with your own eyes was born inside one. Our own sun came from a place like this, somewhere in the spiral arm of our galaxy, more than 4.5 billion years ago. The cloud that made us is long gone now, scattered by the winds of the stars it produced. We cannot visit it. We cannot study it directly. We can only look at other clouds far away and try to imagine what ours might have looked like before everything we know began. This is where the great mystery starts. We can see clouds today. We can see young stars surrounded by glowing disks. We can see fully formed planets orbiting older suns. What we cannot see in full is the connection between them. We do not know exactly what tips a quiet cloud into motion. We do not know why some clouds make a single star and others make hundreds. We do not know why some young stars grow planets at all, and some seem to spend their gas and dust on nothing in particular. The story of how a soft, dim cloud becomes a system of warm worlds is still being pieced together, one careful clue at a time. There are several ideas. One possibility is that a nearby star explodes, sending a shock wave through the cloud and squeezing it until parts begin to collapse under their own weight. Another idea is that the cloud simply grows heavy enough on its own, slowly, with no outside push, until gravity finally wins. Some researchers wonder if the magnetic threads woven through the gas play a larger role than we once thought, holding the cloud up like an invisible net, until something causes that net to slip. The evidence is incomplete. The question remains open. For now, picture the cloud as it was, vast, cold, patient, sprinkled with the ashes of older suns, threaded with faint magnetic fields that hum at frequencies no ear could hear, lit only by distant starlight filtering in from beyond its edges, and by the dim glow of the few warm spots already beginning to stir inside it. Nothing about it looks urgent. Nothing about it looks like the beginning of anything. And yet, somewhere within it, the first quiet pull of gravity is gathering matter together. A knot is forming. A small, denser place is starting to lean inward on itself. That knot is the seed of a solar system. It is the seed of a sun. It is the seed of every planet, every moon, every comet, every distant icy world that will one day spin in slow orbits around a new star. Tonight, as you rest, we will follow that seed. We will watch it slowly turn into a story, and we will sit gently with all the parts of that story we still do not understand. Before we wander deeper into the slow making of worlds, let's take a moment to settle into what a solar system really is. Set aside, for now, the question of how it forms. Picture only the finished thing. A solar system is a star, and everything that quietly belongs to it. Planets, moons, rings, comets, fields of dust, and long, slow rivers of ice. All of it held in place by a single thread. That thread is gravity. Gravity is the gentle pull that every bit of matter has on every other bit of matter. A speck of dust pulls on you. You pull on it back. The pull is so soft that you never feel it. But across the wide dark of space, given enough time, even the softest pulls begin to add up. That is the whisper this section is named for. The first quiet tug of one tiny grain on another, long before any star has lit up. Our own solar system gives us a useful picture. At its center sits the sun. The sun is about 1.5 million kilometers across. If you imagined the sun shrunk down to the size of a beach ball, the Earth would be a small marble sitting about 30 meters away. The marble would carry a tiny grain of sand beside it, which would be the moon. The next planets out would be even further. Neptune, the farthest of the 8, would be over a kilometer down the road. And the loose, icy edge of the system, where comets drift, would stretch farther still, maybe far enough to reach the next town over. That is the scale of one quiet solar system, mostly emptiness, a small bright center, a few specks of rock and gas in slow circles, and a vast, cold halo of leftover material at the edge. Our own system is thought to be about 4.5 billion years old. That number is hard to feel. So think of it this way. If the whole age of the solar system were squeezed into a single day, all of human history would fit into the last fraction of a second before midnight. The sun was already shining for nearly its entire lifetime before any person looked up at it. The planets had already settled into their slow paths. The moon had already cooled. By the time we arrived, the story of formation was long over. What is a solar system made of? In the simplest terms, 2 things: gas and dust. The gas is mostly hydrogen and helium, the lightest and most common elements in the universe. The dust is everything heavier. Tiny grains of carbon, silicon, iron, ice, and other minerals. These grains are smaller than the particles in smoke. You could fit thousands of them across the width of a human hair. And yet, somehow, grains like these are what eventually became mountains, oceans, and the ground beneath your feet. The exact recipe varies from system to system. Some young stars seem to form with rich, heavy disks full of dust. Others form with thinner, gassier ones. Why this variety exists is one of the open questions we will sit with later. For now, just notice the strangeness of the basic idea. A planet with all its weight and stone and weather started as a soft cloud of nearly nothing. The numbers around that cloud are also worth holding gently in mind. A typical star-forming cloud can stretch for tens of light years. A light year is the distance light travels in 1 year, which is nearly 10 trillion kilometers. So these clouds are not small. They are larger than entire neighborhoods of stars. And yet the gas inside them is so thin that, by Earth standards, it would count as a vacuum. A laboratory could not pump air out fast enough to match how empty these clouds already are. This is one of the quiet riddles of formation. The raw material is spread out across distances we cannot picture, in densities we cannot feel, and from that thin, cold, almost nothing, the universe builds suns and worlds. The pull of gravity does almost all the work. But how, exactly, gravity finds its first grip in such a smooth, calm cloud is still a question researchers wonder about. Some think small disturbances start the process. Others think the clouds were never as smooth as they look. The answer is not yet settled. Hold that picture for a moment as you drift. A cloud larger than you can imagine. A dust so fine you would not see it. And a force so soft it can take 10 million years just to begin its work. That is where every solar system starts, with a whisper. Picture the cloud again, that vast, cool drift of gas and dust hanging in the dark between stars. Something has nudged it. Maybe a distant star ended its life and sent a soft pressure wave rolling through space. Maybe the cloud simply grew heavy enough to no longer hold itself up. Whatever the trigger, gravity has begun its slow work, and a small patch of the cloud has started to fall inward. The fall is not fast. In the beginning, it is almost too gentle to notice. A region the size of many light years pulls itself together over hundreds of thousands of years. Atoms drift toward atoms. Cold hydrogen gathers with cold helium. Tiny grains of dust, no bigger than smoke, tumble inward through the quiet. As the cloud falls, something remarkable happens. The whole region had been turning ever so slightly, like a lazy wheel. You cannot see this turning at first. The motion is too slow, the cloud too wide. But as the gas pulls inward, that turning becomes important. Anything that spins and shrinks must spin faster. A skater pulling her arms close to her chest feels this same rule. The cloud feels it too. So the collapse is not a simple plunge. It is a tightening spiral. The center grows denser and warmer. The edges keep falling, but they fall while spinning, and that spin holds them back from reaching the middle directly. Instead of falling straight in, the outer gas swings around again and again and slowly settles into a flat, turning shape. A flattening cloud, a widening disk, a bright thickening core. This is the shape young solar systems seem to take over and over across the galaxy. We see it in dark clouds where stars are forming right now. We see it in the patient images returned by our largest telescopes. The disk is not a guess. It is a pattern repeated in the dark, but the why of it still holds open questions. Why does the cloud collapse here and not over there? Why this density, this temperature, this exact rate of spin? Some researchers think the trigger is almost always a nearby shockwave, the breath of a dying star pushing on a quiet neighbor. Others suspect that many clouds collapse on their own, with no outside push, simply because they have cooled enough to give in to their own weight. Both ideas may be true in different places. The full picture is not yet settled. The timescale alone is humbling. From the first soft inward drift to the first true glimmer of a young star, perhaps 100,000 years pass. To us, that is long beyond any human story. To the galaxy, it is a single slow breath, and during that breath, the temperature of the inner region climbs from just a few degrees above absolute zero to thousands of degrees. The core begins to glow, not yet as a star, but as a warm, dense knot of gathering matter. Around this warming core, the disk takes its final form. It is wide and thin, like a record laid flat in space, sometimes hundreds of times wider than the orbit of our outermost planets. Inside it, the dust and gas are still falling, still spiraling, still working out who will end up where. The inner edge runs hot and bright. The outer edge stays cold and dim. Everything between them is in motion, sorting itself by weight, by stickiness, by chance. One of the quiet mysteries of this stage is how the spin itself behaves. A collapsing cloud should, in theory, spin so fast as it shrinks that the young star at the center cannot finish forming. The spin should fling material outward faster than gravity can pull it in. And yet, stars do form. Something is bleeding the spin away. Magnetic fields threading through the disk seem to carry some of it off. Outflows of gas, shot from the poles of the young core, may carry more. The details remain a working puzzle. Different models give different answers, and observations have not yet chosen between them. So picture it now as you rest. A cold cloud falling for 100,000 years. A slow turning that becomes a faster turning. A wide flatness forming out of a shapeless mist. A warm center beginning to glow. Around that center, a disk wide enough to one day hold every world a system will ever know, every moon, every comet, every ring. None of those worlds exist yet. They are only possibilities, suspended in the turning gas. The collapse has done its work. The shape is set. What happens next, inside the disk, is where the true mystery of planet building begins. For now, the system is only a slow, spinning breath, gathering itself in the dark. At the heart of the spinning disk, something new begins to glow. The center of the collapsed cloud has grown so dense, so hot, that the atoms inside it can no longer resist each other. Hydrogen, the simplest element in the universe, begins to fuse. Two hydrogen nuclei press together and become helium. And in that quiet act of joining, a small amount of mass turns into light. A star is born. This newborn star is not yet steady. It flickers and pulses. It is wrapped in the leftover gas and dust of its own birth cloud, still feeding on the material that falls inward. From the outside, you might not even see it clearly. You would see a glowing knot inside a thick veil of dust, warm in the infrared, hidden in visible light. Yet inside that veil, the engine of a whole solar system has just switched on. The material this young star is made of carries a long story. Most of it is hydrogen and helium, the two lightest elements, made in the first few minutes after the universe began. These two gases drift through space in vast amounts, filling the dark between stars. They were here long before the cloud collapsed. They were here long before the sun. They are, in a sense, the oldest things any of us will ever touch. But the cloud held more than hydrogen and helium. Mixed into it were heavier elements: carbon, oxygen, nitrogen, silicon, iron, gold. These elements were not made in the early universe. They were forged inside earlier stars, stars that lived and died long before our sun ever shone. Inside the hot cores of those older stars, lighter elements fused into heavier ones, layer by layer, over millions of years. And when those stars reached the end of their lives, they scattered their atoms back into space. Some of them died gently, puffing off their outer layers into soft, glowing shells of gas. Some of them died with great force, in bright explosions that seeded the surrounding clouds with the heaviest elements of all: the iron in your blood, the calcium in your bones, the oxygen in the breath you are taking right now. All of it was cooked inside ancient stars and then released into the dark. Our solar system formed from a cloud salted with the ashes of those earlier suns. This is why the question of how solar systems form connects to the wider story of the universe. A young star at the center of a disk is not just a sphere of glowing gas. It is a gathering of inheritance. Every atom in it has a history. Every grain of dust around it carries a memory of older stars. The disk that swirls around the newborn sun is rich with minerals. Tiny crystals of silicates, flakes of carbon, specks of iron, frozen drops of water, ammonia, and methane farther out where it is cold. Researchers still wonder how much of this material came from the original cloud and how much was reshaped by the heat of the new star. Close to the star, temperatures were high enough to melt and even vaporize many compounds. Farther out, ices could survive. Somewhere in between, the chemistry of the disk became layered, varied, complex. Some scientists think much of the water on rocky planets like Earth was delivered later by comets and asteroids that drifted in from the cold outer regions. Others suggest a good portion of it was already mixed into the inner disk from the start. The evidence is still being gathered, and the answer may turn out to be a blend of both. What is clear is that everything links. The iron at the core of Earth was forged in the heart of a dying star. The carbon in every living cell on this planet came from the same kind of source. The water in the oceans, whatever its exact path, was born from atoms made in stellar furnaces and assembled into molecules in cold, quiet places between the stars. The newborn sun and its disk inherited all of this. They did not invent the ingredients. They only gathered them. So when you picture a young star glowing at the center of its dusty disk, picture also the long chain that brought it there. Generations of older stars, their slow burning, their quiet or violent deaths, their gifts of carbon and iron and oxygen drifting outward through the dark. A cloud forming, collapsing, spinning, lighting up. The materials are ancient. The arrangement is new. And what will become of those materials? What worlds, what oceans, what stones is still, in the earliest moments, an open question waiting to unfold. Around the young star, a wide, flat disk of dust and gas now turns in slow, patient circles. From far away, it might look like a soft, glowing record, tilted in the dark, catching the light of the new sun at its center. Up close, it is a place of quiet motion. Tiny grains drift, gas flows. The whole disk hums with forces we cannot see, all working together, all pulling in different directions at once. Gravity is the loudest voice in this quiet room. The young star, sitting at the heart of the disk, pulls on everything around it. Closer in, that pull is strong and fast. Farther out, it grows gentle and slow. This is why the disk spins the way it does. Inner material races around the star in just a few years. Outer material may take centuries to make a single loop. The disk is not one solid sheet. It is millions of nested rings, each turning at its own speed. But gravity is not alone. Pressure also lives inside the disk. Gas wants to spread out. It pushes outward against the squeeze of gravity, holding the disk puffy and soft, like a slow exhale held in place. Without this pressure, the gas would simply fall straight into the star. Without gravity, it would drift away into the cold. The two forces argue gently, and the disk is the shape of their agreement. Heat plays its own quiet part. Close to the star, the inner disk is warm, sometimes glowing red and orange in the dark. Out here, ice cannot form. Only rock and metal can survive. Farther out, the disk cools. Water freezes. Methane and ammonia freeze too. The temperature changes slowly with distance, and this gentle slope decides what kinds of worlds can be built in each layer. The forces of heat and cold sort the disk into zones, almost like the floors of a tall, silent house. Magnetic fields thread through the gas as well. They are invisible lines, woven by the spinning star and by the charged particles drifting through the disk. These fields can grip the gas and tug on it, slowing some parts down and speeding others up. Researchers think magnetic fields may be one reason material falls inward at all. Without them, the disk might just keep spinning forever, never feeding the star, never letting planets form. But the details remain unclear. How strong are these fields? How tangled? Where do they break and snap and reconnect? These are still open questions, watched closely by anyone who studies young stars. Radiation pours from the new star in every direction. Light, ultraviolet rays, and bursts of high-energy particles all wash across the disk. This radiation warms the inner regions. It can also strip away the lightest gases over time, slowly thinning the disk from the inside out. Some theories suggest that nearby stars, if the young system is born in a busy cluster, may add their own radiation too. A close giant star, blazing hot, can erode a young disk from the outside, shortening the time available for planets to form. Whether our own sun grew up near such neighbors is a question we cannot fully answer. Tidal forces add another gentle pressure. When a clump of material grows large enough, it begins to tug on the disk around it. The disk tugs back. These tides can carve narrow gaps where a forming planet sweeps its lane clean. They can also send waves rippling through the gas, spiral patterns that look almost like the arms of a tiny galaxy. Telescopes have spotted these spirals around real young stars, frozen in the slow light of submillimeter cameras. We see the patterns. We do not always know which planet or which clump is making them. All of these forces work on timescales we struggle to picture. Gravity squeezes for millions of years. Pressure pushes back for millions of years. Heat slowly sorts the grains. Magnetic fields stir the gas. Radiation trims the edges. Tides carve and ripple. None of it is fast. None of it is loud. The disk simply turns and turns and turns, and the balance of forces shifts a little at a time, like a wide, quiet machine made of mist. Somewhere inside this balance, the seeds of planets begin to gather. We do not yet know exactly how the first specks find each other. We do not yet know which forces matter most, or in what order. The disk is the workshop, but the tools are still partly hidden from us. For now, picture it slowly spinning in the dark, glowing softly at its center, fading to cold blue at its edges, holding all the worlds that have not yet been born. Picture, if you can, a single grain of dust floating in the dark. It is far smaller than a grain of sand on a beach, smaller even than the dust that drifts through a sunbeam in a quiet room. A typical grain in a young planet-forming disk is about 1 micrometer across. That is 1/1,000,000th of a meter. You could line up 1,000 of them across the width of a single human hair. These are the seeds of worlds. Every rocky planet, every moon, every mountain and ocean and stone began as something this small. The thought is almost too gentle to hold. Now picture the place where they live. The disk of gas and dust around a newborn star can stretch 100 times the distance between the Earth and the Sun. If you shrunk the young star down to the size of a basketball resting on the floor, the outer edge of its disk might reach the far end of a football field. And in all that vast, spinning space, the grains drift like a faint mist. There are not many of them per cubic meter. If you stood inside such a disk, you would not see a thick fog. You would see something closer to the clearest desert air, with only the rarest speck passing by. This is the first mystery of the section. The grains are tiny. The distances between them are enormous, and yet somehow they find each other. Somehow they meet, stick, and grow. Let the scale settle in for a moment. Imagine you are standing in the middle of a large empty stadium. Now imagine that every few minutes, a single mote of dust drifts slowly across the open air, with no other mote anywhere in sight. That, very roughly, is the loneliness of a grain in a protoplanetary disk. And yet, given enough time, those motes are supposed to come together and build something the size of a continent, then something the size of a moon, then something the size of a world. The time involved is hard to feel. Researchers think the earliest stages of grain growth may take only a few thousand years, which sounds long until you compare it to the age of the sun. Our star is about 4.5 billion years old. A few thousand years inside that life is like a single quiet breath inside a long human lifetime. Worlds, it seems, can begin in something close to a whisper. The temperatures across the disk vary wildly. Close to the young star, the inner disk can glow at well over 1,000 degrees Celsius, hot enough to melt rock and vaporize metal. Out in the cold outer regions, temperatures fall to around 240 degrees below 0 Celsius, colder than any winter night on Earth, colder than the surface of Pluto. The same disk holds both furnace and freezer. The grains in each zone face very different worlds, even though they share the same spinning home. The grains themselves carry surprising variety. Some are mostly silicate, the same family of minerals that make up beach sand and ordinary rock. Some are rich in carbon, dark and sooty, like the soft black powder inside an old fireplace. Out beyond the frost line, grains gather coats of water ice and sometimes coats of frozen methane or ammonia. Each grain is a tiny package of chemistry, drifting slowly, waiting. The puzzle of how they meet is genuinely open. One idea is that gentle turbulence in the gas nudges grains together at slow speeds, allowing them to stick when they touch. Another possibility is that grains settle toward the flat middle of the disk, where they crowd close enough to find one another more often. A third line of thought suggests that small eddies and pressure pressure bumps in the gas act like quiet pools, trapping drifting grains until the local density rises. Each idea explains part of what we see. None fully explains the whole. What makes the scale so moving is the contrast. Something almost weightless, almost invisible, almost nothing, is the beginning of everything solid we know. The pebbles on a riverbank, the cliffs above an ocean, the iron in your blood, the calcium in your bones. All of it traces back to grains this small, drifting through a disk this wide, around a star this young. How they truly find each other across such emptiness is one of the open questions this episode keeps circling. The numbers are gentle. The distances are vast. The grains are patient. And the worlds they build somehow arrive. Picture yourself floating just above the disk now, close enough to see its surface in detail. The view is strange and beautiful. Below you stretches a vast, slowly turning sea of dust, glowing softly in the light of the young star. The surface is not smooth. It ripples and waves like the top of a calm ocean stirred by a deep current. In places, the dust thickens into long, dark lanes. In other places, it thins to a faint haze, and you can almost see the star shining through. If you reached out a hand, you would feel grit drifting past your fingers. Tiny grains, no bigger than the dust on a windowsill, tumble slowly in every direction. Some are dark as soot. Some sparkle like flecks of glass. Some are coated in ice, glinting blue and white where the starlight catches them. They move with the slow patience of snow falling in still air. This is the surface layer, where one of the deepest puzzles in planet formation lives. Somehow, these grains must grow into pebbles. The pebbles must grow into boulders. The boulders must grow into worlds. The first step seems simple enough. Dust grains brush against each other and stick, held together by faint static charges and gentle chemistry. Over many slow years, they become small, fluffy clumps the size of sand grains, then the size of peas. But here the trouble begins. Once a clump reaches the size of a pebble, perhaps a centimeter or two across, it starts to behave in a strange way. The gas in the disk drags on it. The pebble feels a slight headwind as it orbits. That headwind robs it of speed. And when an orbiting object loses speed, it begins to spiral inward toward the star. Some researchers call this the meter barrier, though the problem can begin at much smaller sizes. By the time a clump grows to about a meter across, it can drift inward so quickly that it would fall into the star in only a few hundred years. That is far too fast. There would be no time for it to grow into a planet. The puzzle is plain. If pebbles fall into the star before they can become boulders, how does anything ever get bigger? This is the mystery of pebble growth, and the answer is not yet settled. Several ideas compete, each with quiet evidence behind it. One possibility is that the disk is not as smooth as it looks. Hidden inside it may be slow eddies, gentle whirlpools of gas that trap pebbles the way leaves gather in the still corners of a stream. In these traps, pebbles could pile up, bumping into each other often enough to clump together before they drift away. Some images of distant young disks do show bright rings and dark gaps, which might be signs of such traps at work. But the cause of the rings is itself debated. Another idea is called streaming instability. In this picture, when enough pebbles gather in one region, their combined weight begins to drag the gas along with them, instead of the other way around. The headwind weakens. The pebbles slow their inward drift, and then, almost suddenly, gravity takes over and pulls a great swarm of them into a single body, perhaps the size of a small asteroid. Skipping the slow middle steps entirely, it is an elegant idea, and computer models support it. Whether nature truly works this way at every disk, in every system, remains an open question. A third possibility is gentler still. Perhaps the pebbles are fluffier than we imagine. Loose, snowflake-like, mostly empty space. Such fluffy aggregates might fall through the gas more slowly and stick more easily when they meet. There is some laboratory evidence for this, where researchers have built models of dust grains and watched them collide in low gravity. The grains stick in odd, branching shapes, but scaling those experiments up to a real disk is difficult, and the picture is incomplete. It is also possible that several of these processes work together. Eddies gather the pebbles. Streaming instabilities concentrate them further. Fluffy structures help them survive their first collisions. The truth may not be one clean story, but a quiet collaboration of effects, each one doing its small part. For now, floating above this slowly turning sea of dust, the listener can simply imagine the patient question: how does a grain of soot become a stone? How does a stone become a world? The disk holds the answer somewhere in its drifting layers. We have not yet learned to read it fully. The pebbles tumble on, quiet and slow, keeping their secret for a little while longer. Imagine reaching into the young disk and lifting out a single boulder. It would feel rough in your hands, a clumped thing of dust and ice, pocked with little holes where gas once flowed through. From the outside, it might look unremarkable, but inside this humble stone lies one of the deepest puzzles in the story of how worlds are made. We left off with the question of pebbles, those small clumps that somehow survive in the swirling disk. Now the puzzle gets stranger. Pebbles must somehow become boulders. Boulders must somehow become mountains. And mountains must somehow become whole planets. Each step seems simple from far away. Up close, none of it is. The trouble lives in what we cannot see. When you look at a boulder forming in the early disk, the outside is only part of the story. Beneath that crusty shell, there may be loose powder, soft pockets of ice, threads of carbon dust pressed gently together. Some researchers think these early boulders are not solid at all. They may be more like dirty snowballs, fluffy on the inside, held together by the faintest tug of gravity and the soft stickiness of frozen gases. That fluffiness matters more than it sounds. A soft, porous boulder behaves very differently from a hard one when two of them meet. A solid rock might shatter on impact. A fluffy one might squish, absorbing the blow, sticking instead of breaking. One idea is that the earliest worlds were built from these gentle, low-density lumps, which cushioned each collision and slowly grew. Another idea is that they were denser, packed tighter, and that the secret of their growth lies in something else entirely. Both pictures are still being studied. Neither has won. Deeper inside these early boulders, layers begin to sort themselves out. Heavier grains settle toward the center. Lighter ices coat the outside. Tiny channels of empty space, maybe no wider than a hair, thread through the interior. In a sense, a boulder a kilometer wide may already be a small world, with its own crust, its own hidden middle, its own quiet structure. We cannot dig into one to find out. We can only model it on computers and compare what we find to the meteorites that fall to Earth. Those meteorites are our closest clues. When researchers slice them open, they find strange treasures inside. Small, round droplets of once melted rock, frozen mid-motion. Flecks of metal older than the sun itself. Tiny grains of stardust carried in from other stars that died long before our own was born. Each meteorite is a little library, and each page hints that the early boulders were built from pieces with very different histories. How those pieces came together and in what order remains an open question. Some theories suggest the boulders grew quickly, in only a few 100,000 years. Others suggest a slower path, stretched over millions. The difference matters because the disk itself does not last forever. The young star at the center burns hot and bright, and its winds slowly push the gas away. If boulders grow too slowly, the disk vanishes before planets can finish forming. If they grow too fast, the math of collisions becomes hard to explain. Somewhere between these two timescales lies the truth, and we still do not know exactly where. There is also the question of what happens when boulders meet at speed. In a calm corner of the disk, two of them might touch softly and merge. In a turbulent zone, they might smash apart, scattering their pieces back into dust. The disk is not uniform. It has eddies, pressure bumps, quiet rings, and stormy gaps. Some researchers wonder if boulders only manage to grow in special hiding places, sheltered from the worst of the turbulence. Others think growth happens almost everywhere, just at different rates. The evidence from new telescope images of distant young disks is suggestive, but not yet conclusive. What we can say is that beneath the surface of every rocky world you know, including the one under your feet, lies the buried memory of those first boulders, the iron in your blood, the silicates in the stones outside your window, the carbon in the wood of an old chair. All of it once tumbled through a dim, dust-filled disk, sticking and unsticking, growing and breaking, layer upon layer, into something larger. How exactly that something larger crossed the line from boulder to planet, no one has fully worked out. The answer is hidden in the depths of bodies we cannot open, in models we cannot fully test, in the slow, patient mathematics of a process that took place long before any eye was here to watch. Somewhere in the swirling disk around a young star, there is a quiet boundary. It is not a wall. It is not a line you could see if you were drifting through the dust. It is a soft, slow change in temperature, marking the place where ice can finally survive. We call it the frost line, and it may be one of the most important borders in any newborn solar system. Closer to the star, the disk is warm. Heat from the bright young sun bakes the inner regions. Water there cannot stay frozen. It exists as vapor, mixed into the gas of the disk, drifting like a thin steam. Only the most stubborn materials hold together near the star. Tiny grains of rock and metal can survive the heat. Anything icy melts away long before it has a chance to clump. Farther out, the warmth fades. The star's light spreads thinner across a larger volume. Somewhere past a certain distance, the disk grows cold enough for water to freeze onto the dust. Suddenly, the building blocks change. Each grain now carries a little coat of ice. The total amount of solid material jumps. Some studies suggest it can rise by a factor of 3 or 4, simply because water, the most common molecule after hydrogen and helium, finally joins the rocks instead of floating away as gas. This is where the cycles of the disk become interesting. The frost line is not fixed. It breathes. In the earliest years, when the young star is wild and bright, the line sits far out. As the star quiets and the disk thins, the line drifts inward. Then, in some models, it drifts again as the disk cools further. Each shift leaves its mark. Material that froze in one era can sublimate back into vapor in another, depending on how the disk's temperature changes. The boundary pulses in and out, slow and patient, across hundreds of thousands of years. This drifting matters. A planet that begins begins forming on the cold side of the line has icy material to work with. A planet on the warm side does not. That single difference may explain why our inner solar system holds small rocky worlds, while the outer system holds giants wrapped in deep atmospheres. One idea is that Jupiter began life just beyond the frost line, where ice was abundant. With so much extra solid stuff, a young core could grow quickly, then pull in vast amounts of gas before the disk faded away. Without the frost line, perhaps there would be no Jupiter at all. Yet the picture is not as tidy as it sounds. Researchers still debate exactly where the frost line sat in our own early system. Some place it near where the asteroid belt is today. Others argue it was closer in or farther out, depending on how dusty and opaque the disk was. The disk's own shadow shapes the temperature, and that shadow shifts as grains grow and settle. Each assumption nudges the line to a new location. There is also the puzzle of water itself. If the frost line in our young system was beyond Mars, how did Earth end up with oceans? Earth formed on the warm side, where water should have been scarce. One possibility is that icy bodies from beyond the line wandered inward, carrying water in their frozen cores. Another idea is that water vapor diffused inward through the gas, sticking to grains that later became part of our world. The question remains open. The oceans on which life depends may owe their existence to a boundary that drifted past us long before we existed. Other frost lines exist as well. Water is only the first to freeze. Farther out, carbon dioxide reaches its own freezing distance. Beyond that, methane. Beyond that, nitrogen, and even more delicate molecules. Each line adds another layer of solid material, another zone where certain kinds of worlds might prefer to form. Some scientists wonder if the rich variety of icy moons and distant dwarf planets reflects this stacked series of boundaries, each one quietly sorting the chemistry of the outer dark. The frost line, then, is something like a slow heartbeat of the young disk. It expands and contracts. It sorts ice from vapor, gas giants from rocky worlds, comets from asteroids. It decides, in a quiet, patient way, which regions can grow rich and which must stay lean. And though we have many theories about how it moved and where it settled in our own past, the exact rhythm of that boundary is still uncertain. It is one more soft mystery, drifting somewhere in the long memory of our solar system, waiting to be better understood. Inside the warm circle drawn by the frost line, where ice could not stay solid, a different kind of world began to take shape. These were the rocky neighbors, the small, dense planets that would grow close to the young sun. Their story is quieter than the story of the giants, but in some ways it is harder to understand. We live on one of these worlds, and yet we still cannot say with certainty how it came to be. Picture the inner part of the disk. The gas is thinner here, burned and pushed by the star's bright light. What remains is dust made of metal and stone, tiny grains of iron, silicon, and other heavy elements. These grains drift through warm space, bumping into each other, sticking when they touch gently, breaking apart when they meet too hard. Out of this slow shuffle, small clumps grow, then larger ones, then bodies the size of mountains, then bodies the size of small moons. These early objects are called planetesimals, a word that simply means little planets. They orbit the young star in great numbers, perhaps millions of them, sweeping through the inner disk in long, quiet loops. When two of them pass close, gravity tugs at their paths. Sometimes they swing past each other. Sometimes they collide. Over millions of years, the larger ones gather the smaller ones, the way a snowball grows as it rolls down a hill. This stage is called runaway growth. The biggest bodies grow fastest because their gravity reaches farther. They sweep up everything in their orbit, becoming what we call planetary embryos, worlds the size of the moon or Mars. In the inner disk, several of these embryos may form side by side, sharing the warm space close to the star. And here the mystery deepens, because we do not fully know how that crowded nursery settles down into the calm arrangement we see today. One idea is that the embryos kept colliding, merging into fewer and larger worlds over tens of millions of years. The last great impacts would have been violent, beyond anything we can easily picture. Some researchers think our own moon was born from such a collision. When a Mars-sized body struck the young Earth and threw a ring of molten rock into orbit, that ring then cooled and gathered into the pale companion we still see at night. The theory fits much of the evidence, but not all of it. The chemistry of moon rocks looks strangely similar to Earth's, and we are still not sure why. A different question hangs over Mars. It is smaller than expected, much smaller than the steady growth models predict. Some researchers wonder if Jupiter, forming far out beyond the frost line, drifted inward early on and stole material from the inner disk before drifting back out. This idea is sometimes called the grand tack, the picture of a giant planet sweeping in and then tacking away like a sailing ship. If true, it would explain why Mars stayed small and why the asteroid belt is so thinly populated. But other models reach similar results without any grand drift at all, and the debate is still very much alive. Mercury holds its own puzzle. It is unusually dense, with a huge iron core for such a small world. One possibility is that a young Mercury was struck hard enough to lose much of its rocky outer layer, leaving behind a heavy metallic heart. Another idea is that the inner disk was simply richer in metal close to the star, and Mercury formed dense from the start. The two ideas predict slightly different chemistry, and future spacecraft may help us choose between them. Venus, our near twin in size and mass, raises its own quiet questions. Why did it end up with a thick, choking atmosphere, while Earth kept oceans and clear skies? Was the difference written into the planets at birth, or did it emerge later through small accidents of climate? We do not know. What ties all these neighbors together is the sense that the rocky planets did not form in isolation. They grew together, jostled together, exchanged material, and shaped each other through gravity and impact. Earth's water may have arrived in icy bodies flung inward from beyond the frost line. The metals in our blood and bones may have been gathered in collisions whose details are lost to time. The inner solar system we see today is the quiet survivor of a long, crowded childhood. Most of the embryos are gone, swallowed, or scattered. A few worlds remain, spaced gently around the sun, exactly that thinning happened, and why it left these particular worlds in these particular orbits remains a question still being slowly answered. Now we drift outward past the warm, rocky worlds into the cold dark where the giants live. These are the strange ones, the biggest, the most puzzling, the planets that hold most of the mass in our solar system, and yet remain the hardest to explain. Jupiter is the king. It holds more than twice the mass of every other planet combined. If you poured all the worlds, all the moons, all the asteroids and comets into one pile, Jupiter would still be heavier. Its great red storm has churned for at least 400 years. A swirling oval once wide enough to swallow 3 Earths side by side. It has shrunk in recent decades, and no one is quite sure why. Saturn is lighter than water. If you could find a bathtub large enough, the ringed giant would float. Its rings stretch wider than the distance from Earth to the moon, and yet they are barely 30 feet thick in most places. A sheet of ice and dust, vast and gleaming, thinner than a country road. How long they have been there is still an open question. Some studies suggest the rings are ancient, as old as the planet itself. Others suggest they formed only 100 million years ago, when dinosaurs still walked the earth. Both ideas have supporters. Neither has one. The riddle deepens when we ask how the gas giants formed it all. The leading idea is called core accretion. In this picture, a rocky and icy core grew first, slowly gathering pebbles and boulders out beyond the frost line. Once that core reached about 10 times the mass of Earth, its gravity grew strong enough to pull in hydrogen and helium gas from the disk. The planet then ballooned outward, swelling into the giant we see today. But there is a problem. The young disk of gas around a new star does not last long. Maybe 3 million years, maybe 10. After that, the star's light and wind sweep the gas away. Some calculations suggest that growing a rocky core large enough to capture all that gas would take far longer than the gas itself sticks around. The timing is tight, almost too tight. So a second theory waits in the wings. It is called disk instability. In this picture, the gas giants did not grow slowly from the inside out. Instead, a piece of the disk itself collapsed all at once, the way a small cloud might collapse into a star. A giant planet could form in a few thousand years rather than a few million. Fast, sudden, almost like a star that never quite caught fire. Which idea is right? We do not know. It may be that both happen in different systems around different stars. It may be that Jupiter formed one way and Saturn another. The evidence is still being gathered, one careful measurement at a time. The extremes get stranger the closer you look. Jupiter's magnetic field is the strongest of any planet, 20,000 times more powerful than Earth's. Deep inside, the pressure is so great that hydrogen behaves like a liquid metal, flowing and conducting electricity in ways we cannot quite recreate in any laboratory. Saturn's North Pole carries a perfect six-sided storm, a hexagon of winds wider than two Earths, locked in place for as long as we have been watching. Why a hexagon and not a circle remains an open question. Some lab experiments have produced similar shapes in spinning fluids, but no one is sure those experiments fully explain what Saturn is doing. Uranus tips on its side, rolling around the sun like a ball instead of spinning like a top. Something knocked it over long ago, perhaps a giant impact, perhaps a slower gravitational tug from a vanished companion. Neptune, the windiest world we know, blows storms at speeds above 1,000 miles per hour, faster than the speed of sound on Earth. And yet, Neptune sits far from the sun, in a place so cold and so dim that it should, by most measures, be calm. Where does all that energy come from? Some heat seems to leak from deep inside the planet, but the source is not fully understood. These four giants hold most of the mass, most of the moons, most of the puzzles. They are the loud chord in the quiet music of our system, and the simple question of how they came to be fast or slow, from cores or from collapsing clouds, still does not have a settled answer. Tonight, we sit with that. Four enormous worlds gleaming faintly in the outer dark, keeping their secrets while we drift toward sleep. Far beyond the warm zone where rocky planets form, out past the place where the gas giants gather their thick atmospheres, the disk grows quiet and dim. sun, still young, is only a faint point of light here. Its warmth barely reaches this region. The dust that drifts in these outer parts is cold beyond anything we could imagine. It is here that the ice worlds slowly take shape, and it is here that the formation story holds some of its softest, strangest secrets. In this far country of the disk, the building blocks are different. Closer to the star, dust grains were mostly bits of rock and metal. Out here, those grains wear coats of ice. Frozen water clings to them. So does frozen methane, frozen ammonia, and frozen carbon dioxide. Each grain becomes a tiny snowflake, a kind of cosmic crystal drifting in the dark. Some researchers think these icy coatings act like glue, helping the grains stick when they touch. Others suspect the ices behave in stranger ways, fracturing and rebuilding as temperatures shift. The truth likely lies somewhere in between, and the details are still being worked out. The colors of these outer regions are subtle. If you could float there in your imagination, you would see a deep blue darkness, with the central star reduced to a sharp white pinprick. The disk around you would shimmer faintly, more like fog than fire. Soft browns and dim reds would streak the dust lanes, while patches of frost would glint when the starlight grazed them. It is a slow, hushed place, with motion so gentle it almost looks frozen. The ice worlds that form here grow slowly, with less material spread across a much wider zone. The work of gathering takes time. A young ice world might begin as a clump of slushy grains, no bigger than a grapefruit. Over thousands of years, it gathers more. Over millions, it becomes a small body, then a larger one. Some grow to the size of dwarf planets. A few may grow larger still, but the upper limit of how big an ice world can become in the outer disk is something scientists are still trying to pin down. One of the quiet wonders here is the structure of the ice itself. Water ice in deep space does not always look like the ice in your freezer. At very low temperatures, water freezes into what researchers call amorphous ice, a glassy, disordered form. It has no neat crystal pattern. Inside this strange ice, other gases can become trapped, locked in place like memories pressed into wax. When an ice world later warms, even a little, those trapped gases can escape in slow whispers. Some scientists wonder whether this trapped gas plays a role in shaping the thin atmospheres of distant ice bodies. The evidence is still incomplete. There is another subtle detail in these outer reaches. The dust grains out here often carry organic molecules, simple carbon-based compounds built up by radiation and slow chemistry in the dark. Lab experiments suggest that ultraviolet light striking icy grains can produce surprisingly rich mixtures. Whether these molecules survive the long process of building a planet, and whether they ever become something more, remains an open question. The outer disk may be one of the universe's quiet kitchens, preparing ingredients no one will ever fully measure. The shapes of these ice worlds are gentle too, without strong heat to soften them. Many likely keep odd, lumpy forms when they are small. Only when they grow massive enough does their own gravity pull them into spheres. There is a threshold somewhere around several 100 kilometers across, where a body finally rounds itself out. Below that, the world keeps its irregular shape, looking more like a worn stone than a planet. The exact threshold depends on what the body is made of, and that mix varies from place to place in the disk. What scientists find beautiful in the small details is how patient all of this is. The inner planets form in a hurry by cosmic standards. The outer ice worlds take their time. They drift, they touch, they merge. They wear coats of frost that may be older than the star itself, frozen in interstellar clouds long before the disk ever formed. Some of that primordial ice may still exist, untouched, in the cores of distant bodies today. Whether any of those ancient ices still hold the chemistry of the original cloud is one of the gentlest mysteries in this whole story. We do not yet know how much of the old has survived inside the new. The outer dark keeps its secrets close, and the ice worlds drift on, quiet and slow, holding their tiny crystal memories in the cold. For most of human history, the planets seemed like wanderers in a fixed pattern. The word planet itself comes from an old Greek term meaning wanderer. Ancient skywatchers noticed that a few bright points of light drifted against against the slow turning of the stars. They moved, but they moved within rules. Once those rules were worked out, planets came to seem like the most settled things in the sky. For centuries, that idea held. Astronomers built telescopes, mapped orbits, and measured the slow clockwork of our own sun's family. The picture that emerged was tidy. Small rocky worlds near the center, giant gas worlds farther out, each planet sitting more or less where it had always been, tracing the same gentle loops it had traced since the beginning. The solar system felt like a finished painting, hanging quietly on the wall of the galaxy. Then, in the mid-1990s, that painting cracked. Astronomers had been searching for planets around other stars for years, using delicate instruments that could detect the tiny wobble a planet causes in its parent star. The wobble is small. A planet's gravity tugs the star toward us and away from us, shifting the color of its light by a hair. The technique is called radial velocity. It rewards patience and very steady machines. For a long time, it rewarded almost nothing else. Then a signal came in from a star called 51 Pegasi, a sun-like star roughly 50 light years away. The wobble was clear. The math gave a planet about half the mass of Jupiter, but the orbit made no sense. This giant world circled its star in just over 4 days. It sat closer to its sun than Mercury sits to ours. A gas giant roasting in the glare where no gas giant should ever have formed. The discovery, announced in 1995 by 2 Swiss astronomers, did not match anything the textbooks predicted. Gas giants were supposed to form far from their stars, beyond the frost line, where ice could help them gather mass. They were not supposed to live in scalding inner orbits. And yet here was one, undeniably there, repeating its short year again and again. In the years that followed, more of these worlds turned up. Astronomers began calling them hot Jupiters. Some had years shorter than an Earth week. Some had orbits so close their atmospheres were slowly boiling away into long, glowing tails. Each new detection deepened the puzzle. Either these giants had formed in places no one expected, or they had moved. Slowly, the idea of migration took hold. Perhaps young planets did not stay where they were born. disk of gas and dust that fed them could also push them around. A giant planet, still embedded in the disk, might trade energy with the gas around it. Over time, that exchange could drag the planet inward, spiraling closer and closer to its star, until the disk faded and the motion stopped. The hot Jupiters might be the survivors of that long fall. The idea was not entirely new. Some theorists had proposed planetary migration decades earlier, but the work had stayed quiet, treated as a curiosity. The flood of strange new worlds gave it sudden weight. If migration was real, our own solar system might have its own hidden history of motion. Evidence for that history began to gather. Patterns in the asteroid belt hinted at an early reshuffling. The orbits of the outer planets, when modeled backward, seemed to fit better if Jupiter and Saturn had once been closer together. One influential model, sometimes called the Grand Tack, suggested Jupiter once drifted inward, then turned and drifted out again, pulled by its dance with Saturn. Another model, the Nice model, proposed a later shuffle that scattered icy bodies and sent comets raining through the inner system. Each of these ideas is still being tested. None is fully proven. The fossils of early migration are faint, written in the tilts of distant orbits and the chemistry of ancient meteorites. Researchers read those clues carefully, knowing that more than one story can fit the same evidence. What changed in the span of a single human generation was the picture itself. Planets stopped being fixed points in a finished design. They became travelers. They became things that could form in one place and end up in another, carried by forces that have long since faded away. The wanderers of the ancient sky turned out to be wanderers in a deeper sense than anyone had guessed. How far they wandered and how often, and why some systems settle while others scatter, remains an open question. The crack in the old painting has only widened, and through it we keep looking. Moons feel like quiet companions. They circle their planets in steady loops, faithful and old, and most of us picture them simply being there from the start. The truth seems to be stranger than that. Many moons may not have formed alongside their planets at all. They may have grown later from rings of dust and broken stone, like little worlds spun out of the wreckage of older ones. Think of Saturn for a moment. Its rings are wide and bright, made of countless chips of ice, some no larger than a grain of sugar, others the size of houses. From a distance, the rings look smooth and solid. Up close, they are a slow blizzard, drifting and grinding, glittering in the pale sun. For a long time, people assumed the rings were just leftovers, frozen in place since the planet's birth. Now many researchers wonder if Saturn's rings are far younger than the planet itself. Some studies suggest they may have formed only a few 100 million years ago, when an icy moon wandered too close and broke apart. If that idea is right, then Saturn's rings are not ancient at all. They are the soft remains of a moon that no longer exists. And stranger still, the rings themselves may be giving birth to new moons. Spacecraft have spotted tiny moonlets forming at the outer edges, where the ring material spreads and clumps together. Each little moon drifts outward, like a child stepping away from the fire it was born beside. Some researchers think several of Saturn's small inner moons grew this way slowly, one by one, from the slow churn of the rings. The same idea may apply to other worlds. Uranus has a faint ring system and a swarm of small moons tucked close to it. The arrangement is so delicate that any strong nudge would scatter them. One possibility is that those moons also grew from rings long after Uranus itself was finished forming. Another is that they are the broken pieces of older moons that collided and never fully reassembled. The evidence is incomplete, and both ideas remain open. Our own moon may carry a similar secret, though on a much grander scale. The leading theory says that early in Earth's life, a body about the size of Mars struck our young planet. The collision threw a vast cloud of molten rock and vapor into orbit. That glowing ring of debris then cooled and gathered together, slowly knitting itself into the moon we see tonight. If this picture is right, our moon was not born beside Earth. It was born from Earth and from the world that struck it in a furnace of shattered stone. Other theories still compete. Some researchers wonder if the moon formed from two smaller bodies that merged. Others suggest that more than one moon once orbited Earth, and that they slowly combined into one. The chemistry of moon rocks is so similar to Earth's that it puzzles people. A simple impact should have left more of the other world's fingerprint behind. The question of exactly how our moon came together has not been settled. Mars holds its own quiet riddle. Its two tiny moons, Phobos and Deimos, look like captured asteroids at first glance. They are small, dark, and oddly shaped, but their orbits sit neatly in the plane of Mars's equator, which is harder to explain by simple capture. One idea is that Mars once had a ring of debris from an ancient impact, and that the two moons formed from that ring. Phobos is slowly spiraling inward and may one day break apart and form a new ring of its own. Mars, in that case, would gain a soft halo of dust where a moon used to be. The pattern that emerges is gentler and stranger than the old picture. Moons are not always permanent. They can form, drift, collide, shatter, and form again. Rings can be the ashes of old moons or the cradles of new ones. A single planet may pass through several generations of small companions across the long quiet of its life. What we do not know is how common this cycle is across the galaxy. We have only just begun to spot rings around planets that circle other stars. The instruments are not yet sharp enough to see their small moons, if those moons exist. The deeper question stays open: how many of the moons in the universe are first drafts, and how many are the slow rewriting of something that came before? For tonight, it is enough to imagine those soft rings turning, patient and bright, shaping new worlds in the dark. When the busy work of building planets begins to settle, the young system is not left clean and tidy. It is left with leftovers. Rings of stone, fields of ice, scattered pebbles, and frozen worldlets too small to ever become planets themselves. These are the belts, and though they seem like the quiet edges of the story, they may be the threads that hold the whole picture together. In our own system, two such belts stand out. One sits between the rocky inner worlds and the great gas giants, a wide ring of stone and metal we call the asteroid belt. The other lies far beyond the last gas giant, a vast donut of icy bodies known as the Kuiper Belt. Both are made of pieces that never quite joined a planet. Both seem to carry a memory of how the system grew. The asteroid belt is often pictured as crowded, but in truth, it is almost empty. If you flew through it, you might not see a single rock for days. The bodies there are spread across an enormous volume of space, and together they add up to less mass than our own moon. That smallness is itself a clue. Something seems to have stolen most of the material that should have been there. One leading idea is that the gas giant nearest the belt, with its great gravity, kept stirring those rocks so violently that they could never settle into a planet. Every time two boulders tried to merge, a third would come barreling through and shatter them apart. Some researchers wonder if the gas giant once wandered inward, sweeping the belt nearly clean before drifting back out. Others think the belt was always thin and only looks like a leftover because we expected something grander. The question remains open. Far beyond, the Kuiper Belt tells a different story in a different voice. Out there, in the cold and the slow light, sit countless icy bodies. Some are small. Some are large enough to be called dwarf planets. They move in slow, patient orbits, taking centuries to complete a single loop around the sun. Their surfaces are pale and frozen, dusted in nitrogen and methane, sometimes streaked with reddish tones from ancient chemistry. The Kuiper Belt seems to remember the outer system's youth more clearly than almost anything else. The way its bodies are arranged, the way some cluster in strange resonant orbits, the way others tilt at odd angles. All of it hints at a time when the giant planets were still moving, still shoving smaller bodies around like a hand stirring a pond. By reading the patterns in the belt, researchers try to reconstruct that ancient choreography. But the picture is incomplete, and several different histories could fit the same evidence. This is where the symphony begins to sound. The belts are not isolated. They connect the inner and outer worlds through a slow, steady exchange. Gravity from the giant planets nudges icy bodies inward, where they sometimes become comets that warm the inner system with water and dust. Collisions in the asteroid belt send pieces tumbling toward the rocky worlds, some of which fall as meteorites carrying the chemistry of the early sun. The belts are mailrooms, passing parcels between distant neighborhoods. Astronomers have now spotted similar belts around other stars. Many young systems show bright rings of dust at certain distances, glowing softly in infrared light. Some show two belts, much like ours, an inner stone belt and an outer ice belt, with a clear gap between them where unseen planets may be sweeping the space clean. Others show only one belt, or wide, messy disks, or rings tilted at impossible angles. No two seem quite alike. This raises a gentle question. Are belts a normal part of how planetary systems finish forming? A kind of natural punctuation between zones? Or do they depend on the exact history of each system, the wanderings of its giants, the timing of its collisions? One idea suggests that nearly every mature system carries leftover belts, and we simply cannot see most of them yet. Another suggests that some systems clear themselves more completely, leaving little behind. What seems clear is that the belts are not waste. They are the unfinished sentences of formation, holding clues that the planets themselves have long since erased. The rocky worlds were melted and reshaped. The gas giants swallowed and lost much of their original chemistry. But a small, icy body drifting at the edge of the system may still be very close to what it was the day it formed. We listen to the belts the way we might listen to the last soft notes of a song that has nearly ended, trying to hear how the music began. Comets are perhaps the slowest travelers in our solar system. Some take a few years to circle the sun. Others take 10,000 years, or 100,000, or even longer. A single orbit can be longer than all of human history. When a comet passes close to our star tonight, it may be returning from a journey it began before the first cities were built. And when it leaves again, it will not be seen again until long after we are gone. This slow rhythm is one reason comets are so precious to scientists. They carry memories. Comets formed in the cold, outer parts of the young disk, far from the heat of the newborn sun. Out there, ice could survive. Dust could stick to ice. Soft, dark, fragile bodies could grow without being baked apart. most of them stayed out there, drifting in the deep cold, untouched for billions of years. They are the leftovers of leftovers, the pieces that never became planets, never melted, never changed. That is the theory, at least. Some researchers wonder if comets are truly that pristine, or if even the deep cold has slowly altered them over time. Cosmic rays, faint heat from distant starlight, gentle bumps from passing bodies. These tiny forces add up across billions of years. A comet may look ancient and untouched on the outside, while its insides have quietly rearranged. The question of how well preserved these memories really are remains open. There are thought to be two great reservoirs of comets in our system. The first is a flattened ring beyond Neptune, where icy bodies orbit in a wide, cold disk. The second is a vast spherical shell that may surround the entire solar system, reaching halfway to the nearest star. This outer shell is so distant that no spacecraft has ever come close to seeing it. We infer its presence from the comets that fall inward from every direction, as if shaken loose from a great cloud above and below the plane of the planets. How did that outer shell form? One idea is that early in the system's life, the gas giants flung countless icy bodies outward in gravitational slingshots. Some were lost to interstellar space. Others were thrown into long, slow orbits that took them far above and below the disk, over hundreds of millions of years, passing stars, and the gentle tug of the galaxy itself rounded these orbits into a soft, spherical cloud. If this picture is right, the outer comet shell is a kind of fossil record of the chaos that once shaped the planets. But the details remain uncertain. We have never directly observed a body in that shell. We only see the ones that fall in, and every comet that falls in is changing. Each pass near the sun warms the surface. Ice turns straight to gas, lifting dust with it. A tail forms, sometimes two, one of gas, one of dust, both pointing gently away from the sun. With each pass, a little more of the comet is lost. After enough orbits, it may crumble into a dim cloud of debris. Some comets dissolve quietly. Others split in two or three, or break apart entirely. The bright visitors we see tonight will not be the same on their next return. They are slowly using themselves up. This is one of the great slow transformations of the solar system. The comets that formed in deep cold are, one by one, drifting inward and burning away. Each loss is small. Across the lifetime of the sun, it adds up. The solar system today holds fewer comets than it did 4 billion years ago. It will hold fewer still in another 4 billion years. The reservoir is patient, but it is not endless. What we do not know is how fast this draining truly happens, or how it has shaped the inner planets over time. Some researchers wonder whether comet impacts long ago delivered some of the water in Earth's oceans, or some of the organic chemistry that life would later use. Others argue that asteroids carried more of that material, and that comets played a smaller role. The evidence is incomplete. Different comets have different chemistry. Different impacts left different signatures. The story is still being pieced together from samples taken in deep space and from clues frozen in ancient rock. So tonight, while you rest, picture a single comet far out beyond the planets. It moves so slowly that in an entire human lifetime, it would barely shift against the stars. It is falling gently toward a sun it has not seen in 50,000 years. It carries memories older than continents, and it has no idea we are watching, wondering what it will tell us when it finally arrives. In the early years of a young solar system, light is not gentle. It is fierce and restless, a steady pour of color and heat that shapes every world being born around it. The newborn star at the center burns hotter and more wildly than it ever will again. Its surface flares. Its winds rush outward in long, invisible rivers. Even the disk of dust around it glows from within, lit by the slow heat of matter still finding its place. If you could stand far above such a young system and watch it form, you would see light in every direction. The star itself would shine a pale gold white, brighter than our sun is now, but unsteady. Bright spots would bloom across its surface and fade. Long arcs of plasma would rise from its edges, looping out and falling back like burning ribbons. These flares are far stronger than anything our sun gives off today. Young stars send out bursts of X-rays ultraviolet light hundreds of times more intense than mature ones. That fierce light does something important to the worlds being built nearby. It heats the inner disk until rock glows. It strips gas away from young planets before they can hold on. It carves the shape of the system itself, deciding which worlds keep their air and which lose it forever. Some researchers wonder if Mars lost much of its early atmosphere this way, blown off by the wild solar wind of a younger sun. The evidence is still incomplete, but the idea fits what we see in other young systems across the galaxy. Farther out in the disk, the light fades and the colors shift. The inner zone glows red and orange, hot enough to keep iron and silicate dust soft and sticky. Past the frost line, where water can freeze, the disk turns blue and silver in the cooler shadows. Ice begins to coat every grain. The light filtering through this region scatters in soft, pale halos, and the disk itself starts to look like a glowing ring seen edge-on, with a bright inner rim and a long, fading skirt of dust. The young star also pulses. It is not yet steady. Many young stars go through phases where their brightness suddenly jumps, sometimes by a factor of 10 or more, lasting months or years before settling again. These outbursts are called FU Orionis events, after the first such star ever seen behaving this way. During each surge, the star pulls in great gulps of disk material at once, glowing hot enough to bake the inner planets all over again. The deeper cause remains an open question. Some models point to instabilities in the disk. Others suggest a passing companion star giving the disk a sudden squeeze. We are not sure which idea, if any, is fully right. Inside the disk, lightning may also flicker. Studies of meteorites that fell to Earth show small round beads of once melted rock called chondrules. To form them, something had to flash heat dust to thousands of degrees in seconds, then let it cool just as fast. One theory points to shock waves rippling through the disk. Another points to electric discharges, fast, slow lightning between charged clouds of gas. A third suggests bursts of light from the young star itself. Each idea explains some of the evidence and leaves other parts unanswered. The colors of the early years also tell us about chemistry. Sulfur compounds glow faint yellow. Carbon-rich dust looks deep red. Water ice sparkles white. As the disk cools and thins, these colors layer themselves into bands, and the planets growing inside each band inherit a different mix. Mercury, baked close to the star, ended up rich in metal. The outer moons, born in the cold blue zones, ended up wrapped in ice. The simple act of where the light fell decided what each world would be made of. And then there are the shadows. Even in a bright young system, there are dark lanes inside the disk where dust gathers so thickly that no light passes through. These dark rings may be where planets are quietly forming, sweeping their lanes clean as they grow. Telescopes have now seen such gaps in young systems around other stars. Dark grooves cut into glowing disks of dust. Whether every gap holds a hidden planet, or whether some are carved by other forces entirely, is still being worked out. So the violence of the early years is also a kind of painting. Fierce light and fierce winds, flickering outbursts and silent shadows, all of it sculpting the worlds to come. Long before any planet has its first sunrise, the light has already written part of its story, and we are still learning how to read it. Space is a vacuum, and a vacuum cannot carry sound the way air does. A young solar system, in its loudest hour, would still feel silent to a human ear. And yet, the forming system is full of vibration. Shock waves move through dust. Pressure waves ripple through gas. Tremors run through the bodies of growing worlds. If we could translate those motions into something we could hear, the early years would sing in a strange, low chorus. Consider what happens when two young planets meet. In the first 100 million years of a solar system, collisions are common. The disk has spawned hundreds, perhaps thousands, of small worlds. They tug on one another. Their paths cross. Some glance off each other and survive. Others strike head-on and shatter. Still others merge in slow, glowing unions that leave behind a single larger world, hotter and heavier than before. Inside such a collision, the rock itself rings. Seismic waves move through the molten interior, pressure pulses bouncing from core to crust and back again. On Earth, we hear these waves with instruments called seismometers, and we can convert their motion into sound. A large quake, slowed down and tuned for human ears, becomes a deep groan, a long rolling note that fades over hours. A newborn planet, struck by another the size of a small moon, would ring with notes far deeper and far longer than any quake we have ever recorded. One of the great open questions in planet formation is how often these giant impacts happened and how much they shaped the worlds we see today. Our own moon, by the leading theory, was born from such a strike. Something roughly the size of Mars is thought to have hit the young Earth, throwing molten debris into orbit. That debris cooled and gathered into the pale companion that now lights our nights. The idea fits much of the evidence, yet it leaves puzzles. The chemistry of moon rocks matches Earth so closely that some researchers wonder whether the impactor was nearly identical in composition, or whether the collision mixed the two bodies more thoroughly than older models predicted. The question remains open. Other worlds in our system show signs of ancient blows. Mercury's strange density, with its oversized iron core, may be the scar of a glancing impact that stripped away its outer rock. Venus spins backward and slowly, and some researchers suspect a great collision long ago reversed its rotation. Uranus tilts on its side, rolling around the sun like a ball instead of spinning like a top. And the simplest explanation is that something massive struck it early in its life. None of these stories are settled. Each is one possibility among several. The collisions, if they happened, left no witnesses and few clear clues. If you could stand at a safe distance during such an event, you would see a slow, silent flare, a blossom of molten rock spreading outward, glowing droplets cooling into beads of glass as they drift through space. The two bodies, if they merged, would settle into a churning sphere of liquid stone, its surface rippling with waves taller than mountains. Inside that sphere, the vibrations would continue for thousands of years, a long ringing memory of the moment of contact. The disk around the young star carries its own quieter sounds. Spiral density waves move through the gas like ripples on a pond, pressed into being by the gravity of growing planets. These waves are pressure waves, which are the same kind of waves that carry sound through air. In that sense, the disk truly does hum, even if no ear is there to catch the tone. The hum shifts as planets migrate, as gaps open in the dust, as material falls inward and outward. Astronomers studying disks around distant young stars have begun to map these ripples in radio light, watching the patterns and trying to read what the planets within are doing. What remains unknown is how loud, in this loose sense, the early years truly were. We do not know how many collisions a typical young system endures. We do not know whether quiet systems and violent systems produce different kinds of planets, or whether nearly every system passes through a stormy stretch before it settles. The evidence is partial. Each system we observe is a single frame from a film we cannot rewind. So picture it gently. A small world struck by a smaller one, glowing softly against the dark. The deep ring of stone settling into stone. The slow hum of a disk carrying news of unseen worlds. The early system, in its silent way, was full of sound. We are only beginning to learn how to listen. Around every young star, there is a quiet kind of music, not sound exactly, since space carries no air to ripple, but something like music written in numbers, played out in lines of force that loop and twist through the gas around the newborn sun. These lines are magnetic. They thread the disk like invisible strings on a vast, dim harp. And the way they hum shapes how the whole system grows. The math of these magnetic songs is older than the planets themselves. A young star spins fast, sometimes turning all the way around in only a few days. Our own sun, much older now, takes about a month to spin once. The young version spun far quicker. As it turned, it carried its magnetic field with it, sweeping the field through the surrounding disk like a slow, glowing whisk. Where the field met the gas began to move with it. Charged particles cling to magnetic lines the way beads cling to a wire. This simple rule, written long ago in the equations of magnetism, turns into something beautiful when you watch it play out around a baby star. The disk does not just drift in lazy circles. It threads itself along invisible paths, funneling material inward, then flinging some of it back out again in two narrow jets above and below the star. Those jets are part of the song. They can reach across distances measured in light years, where a single light year is the distance light travels in 1 year, nearly 6 trillion miles. A jet from a young star can be longer than the space between our sun and its nearest stellar neighbor, and yet the math behind it is gentle. Spin plus magnetic line plus charged gas equals a thin beam that glows for thousands of years. There are ratios hidden in this music too. Astronomers have noticed that many young stars seem to spin at roughly the same rate, no matter their exact size. Something appears to hold them back, keeping them from spinning ever faster as they pull in more gas. One leading idea is called magnetic braking. The field lines reach out into the slow-moving disk, grip the gas there, and drag against the star's quick rotation. The star pulls the disk forward. The disk pulls the star back. A balance forms, expressed in simple proportions between magnetic strength, mass flow, and spin. Whether this balance fully explains the slow spin of young stars is still an open question. Some models match the observations well. Others leave gaps. The numbers are clean on paper, but the real disks are messy, full of clumps and warps and shadows we cannot yet resolve. The orbits within these disks follow their own elegant law, one written more than 4 centuries ago. The square of a planet's year is proportional to the cube of its distance from the star. A small, tidy relationship. From it, you can predict the timing of an orbit down to the second. Once you know the distance, watch a planet pass in front of its star, note the moment, and you can tell when it will pass again decades later. The universe keeps that appointment. Ratios appear in other places too. Many planetary systems settle into orbital patterns where one world goes around twice for every 3 turns of its neighbor, or 3 for every 5. These are called resonances, and they show up again and again in moons, in rings, in distant exoplanet systems. The same small whole numbers, the same quiet rhythm, repeating across the galaxy. Why nature favors these simple fractions is partly understood. Gravity nudges objects into stable beats, the way a parent's hand can settle a swing into a steady rhythm. But why some systems lock into resonance and others do not remains a softer puzzle. Even the dust grains obey numbers. Their drift inward through the disk follows a balance between gas drag and gravity, a ratio that decides whether a pebble spirals into the star or lingers long enough to grow. Shift the numbers slightly, and you get a different kind of solar system. Shift them again, and perhaps no planets at all. There is a strange comfort in knowing that all of this, the jets, the spin, the orbits, the resonances, can be written in equations short enough to fit on a single page. The cosmos seems to prefer simple rules played on a vast scale. The complications, the surprises, come from how those rules combine across millions of years. The magnetic song of a young star is not loud. It is patient, mathematical, almost shy. And somewhere out there tonight, a new star is humming a song very much like the one our own sun once sang, long before any of this was here to listen. For a long time, we only had one solar system to study, our own. We built our theories around it. We assumed other stars must have followed the same gentle steps. A bright center, small rocky worlds nearby, large gas worlds further out, and a cold ring of ice at the edge. It seemed like a natural pattern. It seemed almost inevitable. Then, slowly, we began to find other systems, and almost nothing looked the way we expected. The first surprises came in the form of giant planets pressed close to their stars. Worlds larger than Jupiter, orbiting in just a few days. Some so close they nearly skim the burning surface. These hot giants did not fit any older model. Gas planets were supposed to form far out, where ice could survive. So how did they end up so close in? One idea is that they drifted inward through the disk, sliding along trails of gas and dust. Another idea is that gravity from other planets shoved them into wild paths that eventually settled near the star. Both ideas might be true in different places. The question remains open. We also found systems with many small worlds packed tightly together. 5 or 6 planets, all closer to their star than Mercury, is to ours. They move in slow, careful resonances, each one tugging the next in a quiet rhythm. Nothing in our own neighborhood looks quite like that. We do not fully understand how such crowded arrangements stay stable. Some researchers wonder if our own inner system once held more planets and lost them long ago. We may never know. Against all of this strangeness, our own arrangement begins to feel rare. A small, rocky world sitting at just the right distance from a steady, middle-aged star, not too close where the oceans would boil, not too far where they would freeze into stone. The slim band where water can stay liquid is sometimes called the habitable zone, the narrow shell of space where a planet might hold seas on its surface. Earth drifts inside that zone and has for billions of years. The balance is finer than it first appears. Our atmosphere is a thin veil, only a few dozen miles deep on a world that is nearly 8,000 miles across. If you shrank the Earth to the size of an apple, the layer of breathable air would be thinner than the skin. That fragile veil holds in warmth, scatters harmful light, and lets gentle blue colors fill the daytime sky. A small change in its makeup over long enough time can shift the whole climate. The distance to the sun matters too. A few percent closer, and the world might run hot and dry. A few percent further, and ice could creep across the seas and never retreat. Our orbit is nearly round, which keeps the seasons mild. Many planets we have found follow stretched, oval paths, swinging from scorching to frozen in a single year. We do not yet know how common circular orbits like ours really are. There is the matter of our large moon, too. It steadies the tilt of the Earth, keeping the seasons from wandering into wild extremes. The leading theory says it formed from a giant collision early in our history, when a smaller world struck the young Earth and threw debris into orbit. If that crash had been a little harder, or a little softer, or had never happened at all, our climate today might look completely different. Whether most rocky planets get such a stabilizing moon is still unclear. Jupiter plays a quiet role as well. Its huge gravity sweeps up some of the comets and stones that might otherwise fall toward the inner worlds. Some researchers think this shield made Earth calmer over billions of years. Others argue Jupiter may have also flung dangerous objects our way, and the picture is more mixed than it first seemed. The debate continues. When you place all these conditions side by side, the gentle star, the round orbit, the thin protecting air, the steadying moon, the distant guardian giant, it begins to feel less like an ordinary outcome and more like a delicate piece of music where every note matters. Change one variable, and the song shifts into something unfamiliar. We do not know yet how often nature plays this particular tune. Among the thousands of planets we have found, only a handful sit in anything close to the right place. Whether they share the rest of the conditions, we cannot say. Each new system we study reminds us how many ways a solar system can be built, and how unusual our quiet, well-tuned home may turn out to be. For a long time, we thought we knew the basic shape of a solar system. A star in the middle, small rocky worlds nearby, giant gas worlds farther out, icy bodies at the edge. It seemed like a tidy pattern. Then we started finding other systems around other stars, and the pattern fell apart almost at once. The first surprise came in the form of hot gas giants, worlds the size of Jupiter, or even larger, hugging their stars in tight, fast orbits. Some of them circle their suns in just a few days. The surface gas on these planets sits so close to the star that it glows. No one expected this. Gas giants were supposed to form far from the star, out past the frost line where ice could survive. So, how did they end up so close in? One idea is that these giant worlds did form far out, then slowly drifted inward through the leftover disk. The gas in the disk drags on them, pulling them toward the star like a slow current. Another idea is that they formed in place, somehow gathering enough material in the hot inner zone to grow huge. A third idea is that other planets shoved them inward through gravity, in long, slow tugs across millions of years. The evidence is incomplete, and each theory leaves something unexplained. The strangeness did not stop there. We began finding planets larger than Earth, but smaller than Neptune, a kind of world we do not have in our own system at all. These are sometimes called super-Earths or mini Neptunes. They turn up everywhere. They may be the most common type of planet in the galaxy. Yet our own sun did not make one. The question of why hangs in the air. Did our young system lose them? Did it never form them? Did something special about our disk skip that size entirely? Then there are the systems with planets in strange dances. Worlds locked into orbital rhythms, where one planet circles twice for every 3 loops of its neighbor. Some systems have 5 or 6 planets all tied together in these patterns, like beads on a slowly turning string. The patterns are beautiful, and they hint that these planets formed gently in the same disk, in the same long stretch of time. But why some systems keep this neat order while others fall into chaos remains an open puzzle. Other systems are tilted in ways that defy the simple picture. Planets that orbit sideways compared to the spin of their star. Planets that orbit backward against the star's rotation. In our model of formation, the star and its planets should spin in roughly the same direction because they came from the same swirling cloud. A backward orbit suggests something violent happened later. A close pass with another star, perhaps, or a gravitational shove from a hidden companion. We can guess, but we cannot yet point to one cause. Some stars host planets that drift far out on long, stretched orbits, more like comets than worlds. Others have planets in tight little clusters near the star and nothing beyond. A few stars seem to have no planets at all, even though their disks looked rich and full when they were young. The variety is staggering. The old idea of one clean formation story now feels too small for what we are seeing. Even the disks themselves keep surprising us. Telescopes that can image these young disks have shown rings and gaps carved into them, spirals winding outward, and dark lanes where something seems to be sweeping the dust aside. Some of those gaps may hold hidden planets too young and small to see directly. Some may be made by other forces we do not fully understand yet. The disks are not smooth platters. They are sculpted, patterned, full of features we are only beginning to map. What all of this tells us is that solar systems are not made on an assembly line. They are shaped by chance, by neighbors, by the particular cloud they came from, by collisions and migrations, and quiet pulls of gravity that stretch across ages. Our own system, with its calm spacing and its tidy frost line, and its small rocky inner worlds, may be one outcome among many. It may be common, it may be rare. We do not yet know where ours falls on that wide map of possibilities. The work of sorting this out is still beginning. Each new system found adds another piece to the puzzle, and each piece seems to ask more questions than it answers. The strange shapes out. There are not failures of our understanding. They are invitations. They suggest the universe builds worlds in more ways than we have yet imagined, and that the full story is still waiting in the dark. Our own solar system has been settling for more than 4 billion years, and still it holds back its answers. The planets move in their familiar paths. The sun pours out its steady light. From the outside, it looks finished, calm, almost complete. Yet, when astronomers look closely, they find unfinished sentences everywhere. There are gaps in what we know, and those gaps stretch both backward into the system's birth and forward into its long, slow future. Some of the deepest puzzles sit at the far edge of the sun's reach. Beyond Neptune, in the cold dark, there are small icy worlds that move in strange, tilted paths. A few of them seem to lean the same way, as if pulled by something we cannot see. One idea is that a large hidden planet wanders out there, far from the sun, shepherding these little worlds with its gravity. Another idea is that the pattern is just chance, a trick of the small number of objects we have found so far. The question remains open. Telescopes keep searching that dark band of sky, and the answer, if it comes, may take decades. Closer in, our system holds quieter secrets. The asteroid belt between Mars and Jupiter looks like leftovers, the rubble of a planet that never quite formed. But the story of why it never formed is still debated. Some researchers think Jupiter's young gravity stirred the region too violently for grains to gather. Others wonder if Jupiter itself drifted inward long ago, sweeping the area clean before drifting back out. The truth may be a blend of both ideas, or something we have not yet imagined. Even the inner planets keep their own riddles. Venus and Earth began as near twins, made from similar dust at similar distances. Today, one is a soft blue world with oceans, and the other is a furnace wrapped in heavy clouds. We do not fully understand why their paths split so sharply. The answer matters because it shapes how we think about every rocky world around every other star. The far future stretches the mystery even further. In about 1 billion years, the sun will grow slowly brighter, warming Earth's oceans until they begin to thin away into space. The continents will keep drifting, gathering, and breaking apart in cycles that have already happened many times. New mountain ranges will rise where there are now seas. Old coastlines will sink. The map of our world will become unrecognizable again and again, long before any deeper change arrives. Then, in about 5 billion years, the sun itself will begin its final transformation. It will swell into a red giant, its outer layers reaching past Mercury, past Venus, possibly past Earth. The inner planets may be swallowed, or they may drift outward as the sun loses mass and its grip weakens. The exact fate of Earth is still uncertain. Some models show the planet surviving as a scorched cinder. Others show it spiraling inward into the bright, bloated star. We do not yet know which path is real. Farther out, the cold worlds will have their moment. As the sun expands, the frost line, the boundary where ice can survive, will sweep outward across the system. For a brief time, in cosmic terms, the moons of Jupiter and Saturn could warm. Their hidden oceans, sealed for billions of years beneath thick crusts of ice, may break open to the sky. What might stir in those waters during that strange, late spring is something no one can say. Eventually, the sun will shed its outer layers in soft, glowing shells and leave behind a small, dense white core. This faded ember will cool for trillions of years, sitting at the center of whatever remains. The outer planets may drift on in long, quiet orbits. New small bodies may form from the ejected gas, or the gas may simply dissipate into the dark between stars. The system will keep changing long after anyone is left to notice. It is worth sitting with that idea for a moment. Our solar system is not a finished painting. It is still being made. Its its early chapters are partly unread, and its final chapters have not yet been written. Every comet, every wandering icy world, every quiet tug of unseen gravity is part of an ongoing story. The universe keeps becoming something new. Stars are forming tonight in clouds we will never visit. Old systems are unraveling somewhere far away. And here in our own corner, the slow work of formation has not entirely ended. Listening for what our system still hides is a way of listening to the future. It is a soft, patient question, and there is no hurry to answer it. Step back for a moment. Let the picture grow as wide as it can. The story of how solar systems form is not one story, but many, told by many voices, each holding a piece of something larger. After more than a century of looking, after telescopes that can see the warm glow of dust around newborn suns, after spacecraft that have touched comets and tasted the wind from other worlds, we still hold competing theories in our hands like stones of different weights. We turn them over. We compare them. We are not yet sure which one is heaviest with truth. One theory says planets grow slowly, grain by grain, pebble by pebble, in a patient drift that takes millions of years. Another says some giant worlds form quickly, when whole regions of the disk become unstable and collapse on themselves in a single dramatic gathering. Both ideas explain some of what we see. Neither explains all of it. The young systems we have watched through our telescopes show rings and gaps that hint at hidden planets. But the planets themselves often refuse to be seen. We are reading the disk like a page in a language we are still learning. There is the question of where planets are born and where they end up. Some hot giants, the size of Jupiter, circle their stars closer than Mercury circles ours. Did they form there in that fierce heat? Or did they drift inward from cooler distances, sliding along the disk like beads on a wire? Both ideas have their champions. Both leave puzzles behind, and our own solar system, with its tidy spacing and its quiet middle years, may be the strange one, the gentle exception in a galaxy full of wilder arrangements. Step back further. The atoms that made the dust, that made the pebbles, that made the boulders, that made the worlds, Those atoms were forged inside stars that lived and died before our sun was born. The iron in the core of the earth, the iron in the blood moving through your body as you lie there, came from the hearts of ancient suns. The calcium in your bones was cooked in stellar furnaces and scattered by supernovae across the dark. The oxygen you are breathing tonight passed through the death of a star older than the ground beneath you. In this way, every solar system is a kind of memory. The cloud that collapses to form a new star carries the ashes of older stars within it. The planets that gather from that cloud are made of recycled light, recycled fire, recycled silence. When we ask how solar systems form, we are also asking how the universe slowly turns its own past into its future. We are asking how stardust becomes stone, and how stone becomes a world, and how a world becomes a place where someone might one day lie awake and wonder about all of this. The competing theories are not enemies. They are different sketches of the same vast picture. The Pebble model and the gravitational collapse model may both be right in different places, at different times, around different stars. The smooth migrations and the violent collisions may both happen in the same young system on different timescales. The truth, when we find it, is likely to be larger than any single idea we hold tonight. It is likely to fold our current theories inside it, the way a wider view folds in a smaller one. And yet, even with all we do not know, the broad outline is steady. A cloud of cold gas and dust slowly gathers itself. A star ignites at the center. A disk spreads and cools. Solid things begin to form. Worlds rise out of the dust. Some stay. Some are lost. The quiet ones settle into long orbits and slow seasons. This pattern repeats across the galaxy, around billions of suns, and has been repeating for most of the age of the universe. You are part of that pattern. The bed beneath you, the air around you, the soft warmth of your own body. All of it was once a thin haze of atoms drifting between the stars. The mystery of solar system formation is, in the end, the mystery of your own deep origin. We do not know all of the answers. We may not know them in our lifetime, but the questions themselves are gentle company on a quiet night. Let the theories rest beside one another for now. Let them keep their disagreements until the morning. The universe has been patient for a very long time. It can be patient a little longer while you let your thoughts grow soft and slow, and let the great wondering settle into something close to sleep. Somewhere out in the dark, a young solar system is finishing its loudest work. The collisions have grown rare. The dust has mostly settled or been swept away. The star at the center has steadied into a calm, patient glow, and the planets have found the paths they will keep for billions of years. After all the heat and motion of formation, there comes a long, soft quiet. Try to picture that quiet for a moment. A pale blue world turns slowly on its axis, its oceans catching the light of a steady sun. Clouds drift across its face in slow white spirals. On the night side, the air glows faintly, and the curve of the horizon fades into stars. Nothing about it is hurried. The world simply turns and turns and turns, the way it has for ages, the way it will for ages more. Out beyond that world, the other planets keep their own slow rhythms. A small rocky neighbor traces a tight circle near the star. A banded giant rolls through its long year, its storms moving in stripes of cream and gold. Farther out, ice worlds glide through the cold, their pale surfaces shining softly in the dim sunlight, each one settled into its place by forces we still do not fully understand. Each one a quiet survivor of a much wilder time. The rings and belts that remain are gentle now. Small stones drift in wide loops, tapping against each other only rarely. Comets sleep in the far cold, holding onto ice that has not melted since the system was young. Now and then, one of them falls inward and brightens for a season, then fades again into the dark. The leftovers of formation are not gone. They are simply resting. And the central star, the warm heart of it all, has grown patient. Its magnetic moods have softened. Its flares come less often. It pours out a steady light that bathes its planets in warmth, asking nothing of them, only shining. Stars like this one can hold their calm for billions of years, long enough for oceans to form, long enough, perhaps, for something to wake up inside those oceans and look back at the sky. We still do not know how often that happens. We do not know how many quiet systems are out there, how many pale blue worlds turn under how many gentle suns. We do not know if our own system is unusual or ordinary, lucky or common. The mystery of how solar systems form is also the mystery of how places like our own come to exist at all. And that mystery is still open, still waiting, still soft at the edges. For tonight, that is enough. The questions can rest with you while you rest. Somewhere out in the galaxy, a disk of dust is just beginning to gather itself into shapes. Somewhere else, a planet that no one has ever seen is finishing its first quiet orbit. Somewhere, an ocean we will never visit catches the light of a moon we will never name. The universe keeps making these things without asking, without hurrying, in the same patient way it has always made them. You are small inside all of this. So is the earth. So is the sun. And there is a kind of comfort in that smallness, a sense of being held by something vast and unworried. The same gravity that pulled the first grains of dust together pulls you gently toward your bed. The same calm that settled over a young world after its formation can settle over you now. Nothing out there is in a rush. Nothing needs you to solve it tonight. Let the image stay with you as you drift. A quiet planet turning, a steady star shining, a dark sky full of soft, distant lights, each one a sun, each one perhaps holding its own family of worlds, each one its own unfinished question. The galaxy turns slowly around them all. It has been turning for a very long time. It will keep turning long after this night ends. We may learn more about how all of this came to be. New telescopes will look deeper. New ideas will replace old ones. The theories that compete now may be replaced by theories we cannot yet imagine. Or some questions may simply stay open for as long as anyone is here to ask them. Either way, the wondering is its own small gift, and you are allowed to set it down now. Breathe slowly. Let the dark be kind. The universe is vast and gentle and still here. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.